In this video, we will be looking at section 1.4, which covers composition of functions. So for a definition, a composition of functions is the function created by using the output of one function as the input of another. So for example, we might write f of g of x. So we take the output from g of x and plug it into function f. Another way we may notate this is f circle g of x, which we read as f composed with g at x. And you can see the way we read these out loud following that. We're going to start our composition of functions by evaluating them. So first off, if we are given f of x equals 2x minus 1 and g of x equals x squared minus 3, we want to find f of g of 0. So we're going to work these composite functions from the inside out. So I want to start with the inside g of 0. So to find g of 0, I'm going to plug in 0 for x into my function g. That's going to be 0 squared minus 3 which is 0 minus 3, which is a negative 3. So now we have g of 0. But I need to go in and plug in negative 3 into my function f because I'm looking for f of g of 0, but we know g of 0 is equal to negative 3. F of negative 3 is equal to 2 times negative 3 minus 1 because I'm just taking my negative 3 and plugging it into f. That is negative 6 minus 1, which is a negative 7. So f of g of 0 is equal to negative 7. Next up, we're looking for g of f of 0. So again, I'm going to start on the inside, which is f of 0. F of 0 is going to be equal to 2 times 0 minus 1, which is 0 minus 1, which is a negative 1. I'm now going to take what I got for f of 0 and plug it in to the function g. So g of negative 1 is equal to negative 1 in parentheses squared minus 3. Negative 1 squared is negative 1 times negative 1, which is a positive 1. We're subtracting 3 at the end, and that gives us a negative 2. Next up, we're looking at f of 0. We already found what f of 0 is. F of 0 we said is equal to negative 1. But instead of plugging it into the function g like last time, I'm plugging this into the function f. So f of negative 1 is equal to 2 times negative 1 minus 1, which is negative 2 minus 1, which is a negative 3. Next up, we're looking for g of 0. We already found the g of 0. We said g of 0 is equal to negative 3. I'm now going to plug that back into my function g. G of negative 3 is equal to negative 3 squared minus 3. Negative 3 times negative 3 is a positive 9, and 9 minus 3 is equal to 6. Finally, we're looking at f of g of negative 1. Starting on the inside, I need to find g of negative 1. I found that before. G of negative 1 is equal to negative 2. Now I'm going to plug that in for my g of negative 1, and I'm looking for f of negative 2. That's going to be 2 times negative 2 minus 1. And negative 4 minus 1 is equal to a negative 5. So we're just working from the inside out. So for example, on this last one, our most inside was negative 1, and I plugged that into my function g. That gave me a negative 2, and I plugged that into the next function out, which was f. We're going to continue evaluating these composite functions. This time we're going to use a table. So it says use the table to find the following values. First up is f of g of 0. So again, I start on the inside finding g of 0. So when x is 0, g is equal to 5. Now I'm going to plug that into my function f. So if I'm plugging 5 into my function f, when x is 5, f of x is equal to 1. Next up, we're looking at f of g of 1. So we start on the inside. If x is 1, what is g of 1? That's 0. If I plug in 0 for x into my outer function f, I get -3. The next one, we're looking at g of f of 2. So I'm going to find f of 2 first. When x is 2, f is 0. I'm going to plug in 0 into my function g. So if x is 0, my g is 5. And then finally, I'm looking for f of 4. So we're going to start with f of 4. f of 4 is equal to 2. Now I'm plugging in 2 into my function f. If x is 2, the function value is 0. So here, you'll see that we're still working from the inside out. We're just making sure to be very careful about our steps. So I'm going to walk us through that last one again just to make sure we're all on the same page. If I want to find f of 4, then I'm starting on the inside finding f of 4. We said that if x is 4, the function value is 2. So I need to replace that f of 4 with a value of 2. Well, then I'm just finding f of 2. That's saying if x is equal to 2, what is the value of the function f? And that's where my 0 came from. So make sure you're starting on the inside and working your way out. Now that we've worked with tables a little bit, let's see if we can do the same with graphs. It says to use the graphs to find the composite, or the following values, and we're working with these composite functions still. First up, we're looking for f of g of -3. So let's start on the inside with g of -3. If our x value is -3, then we need to look on our g function and find the function value. So x equals -3 here. We're on the graph of g at this point. The function value, or the y value there, is 2. So g of -3 is equal to 2. So I'm going to replace my g of -3 with 2, and I'm looking for f of 2. So I need to find where x equals 2 on my function f. That's down here, because my function f is this one. The function value there is -1. Next up, we're looking at g of f of -2. So we start with f of -2. So when x equals -2 on my function f, I'm right here. And that has a function value of 3. So I'm going to replace my f of -2 with 3. And I'm now looking for g of 3. So I need to find the x value of 3 on my function g. It's going to be right here. And that has a function value of 2. Next up, we're looking at f of -1. So we're going to start in the middle, f of -1. When x equals -1, my function value is 1. So I'm now looking for f of 1. When x equals 1, my function value is again 1. So I did plug in -1 for x the first time, and I got out 1. When I evaluated 1 in my function, I got 1 out again. Finally, I'm looking for g of 0. Starting on the inside, we're looking for g of 0. It's going to be down here. That's a function value of -1. So I want to find g of -1, and that's going to be right here, which has a value of 0. So again, really focusing on working from the inside out. Now that we've worked on evaluating functions at values a little bit, we're going to work on taking entire functions and composing them. Please enjoy my entertainment while I remove a hair from this because it's really bothering me. There we go. All right, find composite functions. Find the following functions using f of x equals x squared minus 3x and g of x equals 1 over x plus 2. So what we're going to be doing is we're going to be finding f of g of x and g of f of x. So just like before, we're still plugging one function into another, but instead of using actual numerical values, we're plugging in the entire function. So if I'm finding f of g of x, I'm going to replace that g of x with what g of x actually is. G of x is equal to 1 over x plus 2. So what I need to do is I need to take this 1 over x plus 2 and plug it in for x everywhere it exists in the function f. So that's going to be, I see an x, so I'm going to replace it. 1 over x plus 2. That is squared minus 3. I see another x, so I need to replace it again. I didn't square it this time because my x wasn't squared. The first one was, the second one wasn't. So when I replaced it, the first one was squared, the second one wasn't. Let's see what sort of simplification we can do with this. Well, when something's squared, it means it's multiplied by itself. So I'm going to write that out. 1 over x plus 2 times 1 over x plus 2 minus, and then I'm just going to distribute my 3 through the parentheses. That's 3 over x minus 6. So now I can FOIL this first product. 1 over x times 1 over x is 1 over x squared. My outside terms, I get 2 over x. My inside terms, I also get 2 over x. And then I get 2 times 2, which is 4. We still have our minus 3 over x. Whoops. Minus 6. Now let's see what we can combine. I have a 1 over x squared, 2 over x plus 2 over x, and minus 3 over x. Those all have the same denominator, so I can just combine my like terms. 2 plus 2 makes 4. 4 minus 3 is 1. So I have plus 1 over x. And then a plus 4 and a minus 6 combine to give me a minus 2. That is how this function simplifies. So f of g of x is equal to 1 over x squared plus 1 over x minus 2. In the next one, we want to find g of f of x. So I'll replace my f of x with what it is. And I'm looking for g of x squared minus 3x. So if I plug this in for x everywhere I see it in the function g, I'm going to get 1 over x squared minus 3x plus 2. Honestly, I'm okay with that as an answer. But if you want to have a common denominator so that you can combine these into one expression, or I guess it is an expression, if you want to combine them all into one fraction, then we're going to need a common denominator here. So I'm going to take my 2 and multiply it by x squared minus 3x over x squared minus 3x. And if I do that, then I have the same denominator, so I know I'm going to be able to combine them. We have x squared minus 3x in the bottom. In my numerators, I have 1 plus, if I distribute through, 2x squared minus 3x. Or minus 6x. We're distributing. Look at that. So if I distribute my 2 through, and then if you like things to be in descending order, you can write this as 2x squared minus 6x plus 1 all over x squared minus 3x. So this thing here is a good answer, but what we had before we combine them, that's also a good answer. Whichever one you prefer, go ahead and go with it. We're going to start thinking about composite functions in a slightly different way. The function p of x is equal to the cube root of x squared minus 3 can be expressed in the form f of g of x, where g of x is equal to x squared minus 3. Find f of x. So what we're doing is we are trying to figure out if we plug in g of x into some function f, we should get this out. We already know what g of x is. We know we are plugging in x squared minus 3 into this function f. So since we know what g of x is, I know that my black marker is not happening. Let's try the other one. F of, we know g of x is x squared minus 3. It says that this function p of x can be expressed in this way, so this is equal to the cube root of x squared minus 3. It's looking for us to find f of x. So it's asking, what function do I have to plug this into to get this expression out? Well, we already see the x squared minus 3 is under a cube root. So the function f I'm looking for is the cube root of x. Because if I take this x squared minus 3 and plug it in for x into this function, I get out what I want. So this is what I'm looking for. I know it's a little weird to think about at first, but after you try a few, you'll start getting the hang of it. Next up, we're looking at the function h of x equals the absolute value of 3x plus 4 can be expressed in the form f of g of x, where f of x equals the absolute value of x. We want to find g of x. So this time, I know the outer function. F of g of x is equal to, well, the function f is the absolute value of, and then we have g of x in here. So to find my function g of x, I'm asking myself, what is inside the absolute values? In this case, this is supposed to be equal to the absolute value of 3x plus 4. So what's inside the absolute values? 3x plus 4. So what we're saying here is I instead had the outer function, and I was trying to find the inner function. What do I have to plug into this outer function to get the function they want me to have? And in this case, that's the 3x plus 4. Quite possibly the trickiest part of this section is figuring out domains of composite functions. But if you can remember the two things you're looking for, you'll be able to figure it out. First, you're going to restrict it to the domain of the inner function. And then we're going to have to check the domain of the composed function. And I'll walk you through these. So it says let f of x be equal to 1 over x minus 8, and g of x equals the square root of 2x. Find the domain of f of g of x and g of f of x. So let's start with f of g of x. Thinking about it in terms of what a composite function is, we are taking the function g of x and plugging it into f. Well, I can't plug something in. I can't plug in g of x if g of x itself is not defined. So I need to make sure this inner function, we are in its domain. Because if we're not, then we get something undefined. So starting with the domain of the inner function, my g of x, I need to make sure that thing under the radical is greater than or equal to 0. So I need 2x to be greater than or equal to 0. And if I divide both sides by 2, I get that x has to be greater than or equal to 0. That's my restriction for the inner function. Next up, I need to look at the domain of the composed function. So what is f of g of x? That's when we take g of x and plug it in where we see x is in the function f. So that will look like 1 over, I see an x, so I replace it, the square root of 2x minus 8. So I replace the x with the square root of 2x, and then I subtract the 8. So I see two things in this one. We have a radical, meaning we have to make the thing under it stay greater than or equal to 0. We already handled that here. But I also see a fraction, so I know the denominator cannot be equal to 0. So I need to make sure the square root of 2x minus 8 is not equal to 0. If I add the 8 over, I get that the square root of 2x cannot be equal to 8. I can square both sides. So 2x cannot be equal to 64. And dividing both sides by 2, I get that x cannot be equal to 32. So my two restrictions are that x has to be greater than or equal to 0, and x cannot be equal to 32. So when I write this out in interval notation, the lowest I can go is 0, and I get a square bracket on that because x can be equal to 0. I keep going until I hit 32 because x cannot be equal to 32. I don't include that. I union it with 32 to infinity because 32 is the only positive number that I can't have. Now let's try it the other way. We want to find the domain of g of f of x. So first up, we find the domain of the inner function, f of x. We only have a fraction. I need to make sure that the denominator, x minus 8, is not equal to 0. If I add the 8 over, I get that x cannot be equal to a positive 8. Second, I need to look at the domain of the composed function, so g of f of x. So let's see what that would look like. G of f of x is going to be g of 1 over x minus 8. So if I plug in 1 over x minus 8 into my function g, I'm going to have the square root of 2 times 1 over x minus 8, which is the square root of 2 over x minus 8. So I see both a square root and a fraction here. So with the fraction, the denominator can't be equal to 0. We already handled that case. Now I need to make sure that that fraction, 2 over x minus 8, is always greater than or equal to 0. This is where it gets kind of tricky. I can't multiply both sides by x minus 8 because I don't know if x minus 8 is positive or negative. What I do know is, with this fraction, the numerator is always positive. So the only way for this thing to stay positive is if the denominator is positive, because a positive divided by a positive is positive. So I need to make sure that my x minus 8 is greater than 0. It can't be equal to 0 because then I'd be dividing by 0. This fraction will never be equal to 0 because for that to be the case, my numerator would have to be 0, and it's not. So I need to make sure this denominator stays positive so that this whole fraction is positive. So if x minus 8 is greater than 0, then I get that x is greater than 8. So if x cannot be equal to 8 and x is greater than 8, all I get is x is greater than 8 because it already can't be equal to. So I need 8 to infinity. I can plug in any number between 8 and infinity into this function and I will get out a number. The last thing we're going to look at is understanding these composite functions. It says a city manager has found a function r of p that represents the amount of tax revenue brought in by the population of a city p. It also has found that the population t of y can be estimated using a function such that y represents the number of years since 2010. If we wanted to estimate the tax revenue in 2019, which of the following steps would be helpful? Are we going to solve r of t of y equals 9, solve t of r of p equals 9, evaluate r of t of 9, or evaluate t of r of 9? We are trying to estimate the tax revenue. So do we have a function here that tells us the tax revenue? The city manager has found a function r of p that represents the amount of tax revenue. Yeah. So I'm going to be using this r of p function. All right, so that means that'll be my outer function because I want to find the tax revenue. That should be my very last thing to find. So I know t is not going to be my outer function. So I need to figure out if I want to solve or evaluate. I'm trying to estimate the tax revenue in 2019, which is 9 years after 2010. Y represents the number of years since 2010. So y is going to be equal to 9. This function t of y gives us the population. So if we want to know the population in 2019, we're going to evaluate t of 9. But remember, this function r of p gives us the amount of tax revenue brought in by the population. This gives the population. So I just want to take this population and plug it into my function that gives me tax revenue. So I want to evaluate r of t of 9.